All right, good morning, everybody. Today we're going to finish up 2.5, and that's it. Tomorrow we'll start 3.1. All right. Your test is going to be Monday, June, what's Monday? June 17th. Okay, so Monday we will take time to review for your test, and then it'll be due by the end of the day on Tuesday. So you'll have a window of Monday and Tuesday to work through your tests. And if that timing doesn't work for you, please reach out to me as soon as possible, and maybe we'll work something out based on whatever you've got going on. Okay. Also, be prepared for your quiz, which will be released today, hopefully sooner rather than later after class day. And that will be due by the end of the day on Friday. Okay. Let's see, today is June 12th. All right, we were talking about implicit differentiation. Let's determine slope of the tangent line to, our equation is going to be 3x squared plus y squared equals 100xy at the point we're going to go with 3, 1. So that, am I recording? Okay, good. Yes, I am. This curve is actually something called a lemniscate. And I don't know a ton about this curve or what it does for us or why it's important or what its applications are, but I think it looks pretty cool. It's like a little sideways 8. Something like that. And then the 0.31 is over here. So we're looking for that slope. All right, so our left side, 3x squared plus y squared equals 100xy. Notice, unlike the examples we had yesterday, we don't have just a constant over on the right side of the equation, right? Like, I think all of our examples yesterday had a constant over there, so we had a 0 when we took the derivative, okay? In this example, we're just going to take the derivative of both sides, and neither side is going to be 0, and that's okay. We're still going to be able to solve it for dy dx in the end, right? Our left side needs a chain rule because we have a bunch of stuff in there to a power. And then our right side is going to need product rule because we have the x times the y. Okay, so for our left side, I'm going to just have that 3 tag along. Okay, and then our outside function, we've got a bunch of stuff to a power of 2. Okay, chain rule says differentiate the outside. Okay, the outside function is something to the power of 2. So the 2 is going to swing down here to get multiplied by that 3. And then the power will drop down by 1. I need to keep my inside the same. So we've got an x squared plus y squared. And then I'm going to multiply by the derivative of the inside. Okay, derivative of x squared is 2x plus derivative of y squared. Treat the y like an x, and then multiply by dy dx. Okay, that's the derivative of my left side of the equation. For the right side, I'm going to copy down the 100, and then I'm going to go ahead and make a big set of parentheses so that I remember that the 100 has to be multiplied by everything on the right side. Product rule says, put the reference card up here for you. Product rule says derivative of the first, keep the second. keep the first, derivative of the second, or any rearrangement of those that you want. You know, we know that addition and multiplication are both commutative, so there's some rearranging that you could do here if it were convenient. Okay, so let's see, derivative of the first, derivative of the x is 1 times, keep the second, so the second is y, plus keep the first, so keep the x, times derivative of the second. And the derivative of y is, don't overthink it, the derivative of y is dy dx. Okay, so there it is with the derivative taken on both sides. At this point, what I need to do is get the dy dx alone. So I need to solve this for dy dx. And that's going to get a little bit ugly. So this is a 6x squared plus y squared, and then 2x plus 2y dy dx equals, and then over here I'll write 100 y plus x times dy dx. Okay, so the left side, we're going to have to FOIL that out so that we can factor off a dy dx. And then we're going to want to distribute over here on the right. All right, so I'll do 6 and then open up big parentheses so I don't lose my 6. We've got first x squared times 2x will be 2x to the third. Outer is x squared times this term here, 2y dy dx. So I'll write that 2x squared y dy dx. So that's this one times this one, that's your outer. Plus your inner is 2x y squared. Plus the last is going to be the y squared times 2y dy dx. So it'll be 2y to the third dy dx. That's just the left side. Let me just check and make sure I don't have any little mistakes here. That can happen. Happens to the best of us. Okay, that looks good to me. Right side, I'm just going to distribute the 100. So 100y plus 100x dy dx. You guys know the song? I think it was Beyonce. I'm not even sure now. It was popular in the 2000s. It was like, to the left, everything you own in a box to the left. That's what we're gonna do here. We're gonna take all of the dy dx's and we're gonna send them over to the left side of the equation. I'll do that after I distribute the 6 through, though. That'll make it easier. So 12x to the third, 12x squared y dy dx, 12xy squared, and 12y to the third dy dx. There we go. Okay, so things with dy dx's are going to go to the left. Things without are going to go to the right. So let's see. This is going to stay put. So it's plus on the left, plus on the left, because they're already on the left. They're going to stay on the left. These ones are going to move to the right, so they'll become negative. This one will stay on the right, So that's plus. That one's going to move to the left. So that's minus. I don't know if those little arrows help or not. Okay, so 12x squared y dy dx plus 12y to the third dy dx, and then minus that guy, 100x dy dx. Okay, so that's my left, left, left. And then everything on the right is going to be, I've got the negative 12x to the third, negative 12xy squared, plus 100y. Okay, so which mathematical legal move are we doing here? We're doing legal move number 3. Do the same thing to both sides. I just skipped the steps of showing it all out, right? Like I'm subtracting 12x to the third from both sides so that it's gone on the left and it shows up as a negative on the right. Okay, now from the left side, I can factor out the dy dx since that's what I want to get all alone by itself. So I'll have 12x squared y plus 12y to the third minus 100x equals, and then let's keep that right side just as it was. Okay. Now I want to divide both sides by this stuff in parentheses here. That'll get the dy dx by itself. Okay, so we get cancel there. And we have dy dx equals negative 12x to the third plus 12xy squared plus 100y divided by 12x squared y plus 12y to the third minus 100x. All right. Should we try? What do 12 and 100 have in common? 4. Okay. I think I'm not going to bother simplifying this because the final answer that we're looking for is based on plugging in 3, 1 anyways. And so it's going to cancel when we plug in and it'll work out fine. Again, like on a test, 7, 6. What about 6? You saying you want to take 6 tests instead of 4? Yeah, Daniel wants more tests. Man, you're going to be popular with this class, aren't you? Well, all right, anyways, So we're going to be plugging in 3, 1 here, and then we'll get our cancellations there. On your quiz or your test, honestly, I would accept this answer. I'm not going to mark you off for not canceling out your greatest factor there. That's not a big deal. Hopefully your WebAssign would accept it like that if this were the question that you got. Okay, so let's let x equal 3 and y equal 1. Are you saying the answer is 6? We'll see. Okay, so we're going to have negative 12 times 3 to the third plus 12 times 3 times 1 squared plus 100 times 1 divided by 12 times 3 squared times 1 plus 12 times 1 cubed minus 100 times 3. And mental math, you get 13 over 9. No, I didn't just do that in my head. I had it worked ahead of time. Okay, so because the question was asking us to determine the slope of the tangent line, our final answer is just this number here, 13 over 9. And that number makes sense with the graph that we sketched over here. That little sideways 8 definitely looks like it should be a positive slope over there in the, that lower right of the first quadrant. All right. You got it, or are you still writing? Okay. Next example, let's do sine of xy equals pi over 4. Okay, so what we've got here is a product on the inside with a sine function on the outside. So there will be a chain rule involved and there will be a product rule. Okay, so my outside function is sine. My derivative of sine is cosine. I'm going to keep that inside the same and then multiply by the derivative of the inside. Derivative of the inside is going to call for product rule. Okay, so let's keep the first derivative of the second plus derivative of the first, keep the second. So there's the left side. Right side, derivative of this is just a constant, it's pi over 4. So the derivative of the right side is 0. All right. Now we want to dig that dy dx out of there so that we can solve for it. I'm going to distribute this out. So I'll have x cosine of xy dy dx plus y cosine of xy equals 0. All right, so then I'm going to put everything with the dy dx on one side and everything else on the other. So that'll go to the left and stay positive. This is going to move over to the right and become negative. So x cosine of xy dy dx equals negative y cosine of xy. Yeah, and then let's divide by x cosine of xy on both sides. So then that cancels. We actually get that to cancel as well. So we have dy dx. Oh, and this kind of comes out nice. Negative y over x. And that'll be true where x is not equal to 0 and cosine of xy is not equal to 0. Okay. Next example, I'm gonna do something kind of cool. I'm gonna look at the function y equals x minus 2 squared over x squared plus 1. You probably look at that and go, but Emmy, this is already solved for y. We don't need implicit differentiation here. It's ugly, but I know how to do this. This is ooh, what's going on here? We have a quotient rule. It's a big quotient rule where both the high and the low are going to involve a chain rule. Okay, this is ugly, but it's doable. Well, guess what? I'm actually going to use implicit differentiation here to get this derivative to come out nice in kind of a sneaky way. I'm going to use mathematical move number 3, doing the same thing to both sides of an equation. I'm going to take the ln of both sides. So ln of y equals ln of x minus 2 squared over square root of x squared plus 1. All right. I can do that. I can take the ln of both sides of any equation I want. Now, here's the cool thing. This is why I want to do this, because I've got all those neat properties of logarithms that are going to make this expand out. The logarithm here is going to get rid of my chain rule and my quotient rule. So ln of y equals, all right, well, a quotient turns into subtraction. Ln of x minus 2 squared minus ln of, and I'm going to choose to write this square root as a 1/2 power. All right. What else happens? Exponents become coefficients. So equals 2 ln of x minus 2 minus 1/2 ln of x squared plus 1. Okay. Oh, good morning, Jeremiah. Now, what would you rather take the derivative of? This quotient rule with 2 chain rules inside of it, or, I mean, maybe you think the logarithms are scary, but once you get used to them, they're really not, right? Taking the derivative of that guy right there, he's actually pretty friendly. Okay, so let's take the derivative of both sides. The derivative of all of this nonsense. Okay, so derivatives of logarithms. The derivative of ln of x is 1 over x. That's the basic version of it. And then as we talked about yesterday, if you want the derivative of ln of some inside function, what you're going to do is you're going to do the derivative of the inside over keep the inside. Okay, the derivative of an inside function is derivative of that inside over keep the inside. The derivative eats the logarithm. The derivative makes the logarithm go away. All right, so applying that here, what's on the inside? The y is on the inside. So the inside becomes your denominator. Your numerator is the derivative of the inside. And the derivative of y is dy dx. Okay. Now taking the derivative of the right side. Okay, so this 2 will tag along times, okay, now chain rule here. So what's my inside? X minus 2. My derivative of the inside, derivative of x minus 2 is 1. Minus 1/2 times, keep the inside, put it on the bottom, x squared plus 1. Derivative of the inside will go on top. So derivative of x squared plus 1 is 2x. Right? All right, let me clean this up a little bit.
Where did the 2x come from again?
This 2x,
Yes.
it's the derivative of x squared plus 1.
Okay, that makes sense.
Yep, so our following this rule here, the inside is x squared plus 1, derivative of the inside is 2x. So dy dx over y, let's write 2 over x minus 2 minus, oh, we get a cancel here, x over x squared plus 1. Okay, we're almost there, but we want to get this dy dx alone. So what we're going to do is we're going to multiply both sides by y, but we want this to be in terms of x, right? Like we started out with a nice clean y is in terms of x, y is alone, and then there's only x's over here. So hopefully we're going to be able to end that way as well. Dy dx equals some expression with x's only, no y's. Okay, so I'm going to take this y, I'm going to multiply both sides by y so that it goes over here. So dy dx equals y times 2 over x minus 2 minus x over x squared plus 1. Okay, so I have dy dx alone, but I have a y on the right side of the equation that I don't want. However, if I use legal mathematical move number 4, I can get rid of that y. I can put that y there in terms of x's instead. Okay, so replace something with something equal. Well, what is y equal? We said in the beginning what y equals. This is y. Y equals this. So anywhere I see a y, I can replace it with this. Okay, so dy dx equals x minus 2 squared over x squared plus 1. And I'll just put those blue parentheses around it so that we know that that's the y times, and then I'll just keep everything that's inside here. Okay, there we have it, a perfectly good derivative. I agree. This is a beautiful way to derive it. It comes out much nicer, and there's not as many like little nitty gritty like, oh, did I remember the chain rule here? Did I remember? It's the in my opinion, the logarithmic differentiation does make things a lot easier. Okay. So if you had done the quotient rule, chain rule version of this problem instead, your answer might not look identical to this. Maybe you would get the version where these denominators are combined and everything's carried through. But you should get an equivalent answer. Something that becomes equal if you manipulate it with algebra. Okay. On a quiz or a test, if it says specifically to use logarithmic differentiation, then you have to do it by logarithm differentiation in order to get full credit. Okay. Even if your WebAssign initially marks it right, if I see in your scratch work that it's asking for logarithmic and you don't do logarithmic, you're not going to get full credit. If it doesn't specify a method, then it's your choice. You can decide whether you want to do it in a traditional way or whether you want to use the logarithmic differentiation. Right? Do you guys need another minute to write down all that, or do you got it? Good. All right, so logarithmic differentiation. Let me write down the steps for you.
Question.
Mm-hmm.
Uh, when we are deriving, you don't need to see in this case, the y. If I let the equation in terms of y is not correct.
If you left that, if this was your final answer,
Uh-huh.
I would give that a 4 out of 5. Because if I were to then ask you for the slope of the tangent line to this curve at x equals 3 or some x, whatever you want to pick, you would know how to plug in 3 here and here and here. But then in order to figure out what y is when x equals 3, you'd have to go back to that original function anyways. So it's just better to put that back here. Now, if you're doing an implicit differentiation where it may or may not be an equation that can be solved for y in the first place, in that case, leaving y's in your final answer is perfectly acceptable because you might not be able to get that y in terms of something else.
Thank you.
But in this case, because it was already originally a function of x, we want your derivative to be a function of x as well. Good question. Okay, so steps for logarithmic differentiation. First thing you're going to do is take the ln of both sides. Then you're going to use your properties of logarithms to expand it. Okay, so you'll have ln of one jumbled mess, and you want to take that jumbled mess and spread it out as much as you can. Step 3 is implicit differentiation. And when you do this, remember that the derivative of ln of y is going to end up being dy dx over y. And remember that the derivative of ln of any inside function is the derivative of the inside divided by the inside. once you've crunched through taking the derivative of both sides of the equation, term by term, you're going to solve for dy dx. Okay. Once you've got dy dx alone, you want to get everything in terms of x by replacing the y with the original function. All right. Here's another example. Y equals x to the x. That's kind of a weird function. You can't use power rule here because power rule only applies when you've got an actual number up there. So power rule might make you think, okay, the exponent swings down, I keep the x the same, and then I drop the degree by 1. That doesn't end up working out. Turns out for this function, logarithmic differentiation is really the only way forward, the only way that I can think of. So let's do it. Ln of y would equal ln of x to the x. Okay, now the power rule for differentiation can't swing down that x, but a logarithm can. Logarithms swing down exponents without taking derivatives. So we'll have ln of y equals x times ln of x. Okay, now this is something we can work with. This is a product rule here. Right? So taking the derivative of both sides, the derivative of ln of y is dy dx over y. Dy dx over y equals product rule here. So derivative of the first is 1 times keep the second. Okay, and then keep the first times derivative of the second. Derivative of ln of x is 1 over x. So that term over there is just 1. Multiplying the y over to the right side, I'll have dy dx equals y times ln of x plus 1. And then the last thing to do is take that y and substitute back x to the x. So dy dx equals x to the x times ln of x plus 1. This function here, x to the x, this is this type of function is one of the fastest growing functions that you can think of, right? Like when you think of something growing fast, we often think of exponentials, but this is faster than an exponential. This grows faster than e to the x, because if you think about it, in an exponential, what's being raised to a power is a static number, a number that's not going anywhere. Okay. Here, not only is the power going to increase, but also the thing that you're raising to that power is increasing as well. This is faster than exponential growth, right? Factorials also grow really, really fast, right? Like if you try to type factorials into your calculator, usually your calculator is going to quit on you somewhere in the 80s or 90s, right? Like if I take my calculator here and try to factorial 100, it can't, it stack overflows. It's saying this number is so big that I can't even handle it. 80 factorial. Yeah, it won't. Okay, what can we do? Not much. Okay, so 50 factorial is 3.04 times 10 to the 64 power. So 3.04 times a 1 and 64 zeros. What you got, Daniel?
So can we represent factorials with x power x instead of the other sign? I don't know how to say it in English with the oh Jesus. Let me write.
Sure. X power x. Okay, so Daniel is thinking, is it the case that x to the power x, is that equal to x factorial? No, so I'm showing how big factorial gets and how quickly x to the x is actually a lot bigger. Let's think about like if I try to do let's just look at 8. 8 is a pretty friendly number. We're comparing 8 to the 8 with 8 factorial. This is 8 times 8 times 8. There's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 to the 8 is that. And then 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. Okay, both of them have 8 factors, but this one's got bigger factors. So in fact, factorial grows really, really fast. Like we can't even, stack overflows beyond 50 somewhere. Like we couldn't do 60, 70, 80 because it stack overflows, right? So factorial gets huge really, really fast, but x to the x gets even bigger, even faster. That's why I say this is one of the biggest functions we can imagine. This, if you want to talk about something increasing really, really fast, this is pretty much the fastest one. It's the cheetah or the peregrine falcon of the function world. That was just don't worry about x to the x too much. I mean, it was just that was a nerd out, to be honest. What I care about right now is, do you know how to do logarithmic differentiation? But I just wanted to nerd out on this really cool function for a minute.
Wait, you're a nerd? I
You
never
didn't-
knew that.
Hey, my husband didn't realize I was a nerd
Yeah, we've been
until
together
today.
12
Yeah.
years, and I just now realized you're a nerd.
Yeah, that's what I get for teaching from home. Now my husband discovered my huge secret that I'm a nerd that he never could have imagined before, because it wasn't abundantly clear before today. All right. Let's do one that this one's a little bit ugly. I haven't even worked this one ahead of time. I wrote down like, oh, let's write down a function that's going to be ugly to do without logarithm differentiation. So, hold on to your butts. E to the x sine squared of x plus 1 over 1 plus 1 over x to the x. It's going to be fun. All right. So, the numerator is stuff that we could deal with chain rule and product rule. But this one, because you've got a function to a function, I'm pretty sure the only way to do the derivative of the denominator is with logarithmic. So let's do it. ln of both sides. ln of y equals ln of e to the x square root of sine squared plus 1 over 1 plus 1 over x to the x. Okay. The right side is going to break into 3 different pieces. That one, and that one. Well, ln of e to the x is actually just x. ln of e to the x equals x because the ln, the logarithm, and the exponential, they undo each other. They're inverse functions. Okay, for this guy, it's in the numerator, so it's going to get a plus ln of, okay, the 1/2 is going to swing down, pop out front, and then we'll have sine squared of x plus 1. Now you might be tempted, you might be excited to try to get this 2 to swing down to the outside as well, but unfortunately we can't because it's tied up with that plus 1 there. So this argument inside of that logarithm right there, it's going to have to stay put where it is. This one cannot be expanded any further. Plus, actually minus, this guy's in the denominator, so that's going to be minus the x would swing down, and then we'll have ln of 1 plus 1 over x. Okay, so that's the logarithm part. We haven't done any calculus yet. All we've done here is algebra. The calculus part comes when we take the derivative of both sides. Okay, so left side, I'll have dy dx over y equals, now go term by term, derivative of x is 1 plus 1/2 times, inside goes on the bottom, derivative of the inside goes on top. Okay, so sine squared x plus 1. That sine squared x, you can think of it as a sine of x quantity squared, right? So this is going to need chain rule. I think we did a sine squared before. Swing down the 2. Keep the inside the same, times the derivative of the inside. And then the derivative of the 1 is just 0. Okay, so derivative of the inside is 2 sine of x cosine of x. All right, last one. This one is going to call for a product rule. So using x and then ln of 1 plus 1 over x. So this guy's easy. The derivative of x is 1. Derivative of this guy, okay, we're going to take the inside, copy it on the bottom. Derivative of the inside on top. Okay, derivative of 1 is 0. Derivative of 1 over x. Okay, because 1 over x is x to the negative 1. We're going to swing down the negative 1. And then we're going to drop the power by 1. Okay. Now let me clean this up a little bit. The x to the negative 2 here, because that's a negative exponent, it wants to go down in the basement. Okay, so if I put this guy down below, I can increase the powers of both of those terms by 2. So that'll be negative 1 over x squared plus x. Okay, because what I did there is basically multiply by x squared over x squared and distribute. Can you see that? All right. So this is the derivative of just this piece here. Now for the derivative of all of that, I'm going to do product rule over here. So minus, so they're both going to be negative. I need this times that. And then this times that. That was pretty fun. Okay, what happens next? We get cancel there. You can factor out an x here. So that'll be 1. That'll be x, and that'll be 1. And then we're going to multiply both sides by the y. So dy dx equals y times 1 plus sine cosine over sine squared plus 1 minus, this is 1 over x plus 1 minus ln of 1 plus 1 over x. Okay, last step is to put the y back. So dy dx equals recopying the original equation, the original function for y, e to the x square root of sine squared plus 1 over 1 plus 1 over x to the x times all that nonsense. Oh, okay. That was intense. Definitely watch your parentheses. If you drop parentheses along the way, you're gonna run into some trouble. So get good at knowing when to put parentheses around things and not lose them. I don't think I put one as remotely intense as this on your homework or anything like that. I just wanted to have some fun with it in class today. Here's one that's a little bit more reasonable. E to the xy equals x sine of y. And this one, arguably, maybe we'll do this one both ways because I'm not actually sure. Does this come out nicer if we do logarithmic, or does it come out nicer if we do it regular? Let's see, regular. So just implicit differentiation on both sides without taking the ln first. Okay, so e to something says the derivative is e to that same inside times the derivative of the exponent. Okay, so derivative of x times y, I need product rule there. That'll be x dy dx. So derivative, or keep the first derivative of the second. Derivative of the first is 1. Keep the second. That's the derivative of the left side. Equals product rule over here. Let's keep the x and then find the derivative of sine of y. So the derivative of sine of y is going to be cosine of y, but because of chain rule, we tack on a dy dx, the derivative of the inside. Okay, so that's keep the first derivative of the second. Now we're going to keep the second times the derivative of the first. Okay, derivative of the x is 1. So just a sine of y over there. All right. Now to get dy dx alone, we're going to distribute this and then send all the dy dx's to the same side. So it'll be x e to the xy dy dx plus y e to the xy equals x cosine of y dy dx plus sine of y. So left side plus, right side negative. That'll get negative as we switch. This will stay positive on the right. So x e to the xy. I'm going to jump right to factoring the d. I think you guys are pretty good with your algebra skills. So I'm gonna jump right to factoring out the dy dx. So this term is going to contribute the x e to the xy. This one will do a negative x cosine of y, coming over there, equals, that guy will go here, negative, plus sine of y. So we have dy dx equals negative y e to the xy plus sine of y over x e to the xy minus x cosine of y. And I don't think there's anything we're going to be able to do to simplify that. Okay, so that wasn't too bad doing implicit normally. You know, it's like, oh, I'll take it. Let's see if we like logarithmic better for this question. I don't actually know what we're going to decide we like better. Sorry, did you get all that down or did you need another minute? Good. Okay, so doing it logarithmic, we'll get ln of e to the xy equals ln of x sine of y. All right, well, ln of e to the xy is just xy. The ln and the e to the undo each other. The right side will have ln of x plus ln of sine of y. And that's as expanded as it's going to get. Okay, so let's take the derivative of both sides. Derivative of the left side requires product rule. So we'll have x dy dx. So keep the first derivative of the second. Derivative of the first, keep the second. So x dy dx plus y equals derivative of ln of x is 1 over x plus, okay, the inside is going to go on the bottom just as you see it. So sine of y on the bottom, derivative of that on top. So the derivative of sine is cosine times the derivative of inside, which is dy dx. You too, Jeremiah. See you later. All right, so stay on the left, stay positive. Move to the right, become negative. Stay on the right, so you're positive. Move to the left, so you become negative. So we have dy dx. This one contributes an x. This one contributes a negative cosine of y over sine of y equals 1 over x minus y. So dividing both sides by that stuff in parentheses there, we have 1 over x minus y times this nonsense, which instead of dividing, because it's got a fraction in it, I'll just put a -1. So our answer looks different, but it should be equivalent, those two answers. I think that, so we would want to multiply by sine of y over y. And then it looks like, yeah, when you distribute that through, that makes sense. I'm not going to go through the algebraic steps to show it, but my glance at this tells me that these are likely going to end up equivalent. If our work was all correct, then of course they're equivalent, but it's just not obvious to see it right away. All right, that's a wrap for Module 2. So the stuff that is on your Module 2 test ends right here. So tomorrow we're going to do more stuff with derivatives, but it will not be on the test because it'll be part of Module 3. All right. Daniel, did you bring any homework questions for me today or anything? Okay. And I didn't get any in my inbox or anything like that. So yeah, we're gonna call it quits for today. Remember that there's a couple homeworks that are due tonight from a few days ago or whatever. So definitely be sure to check those out and get through those. Let me know if you've got questions, reach out. We can do a Zoom call. We can do an appointment. We can meet on campus if you like, or I could send you a video or just reply to your message. Hit the Ask My Instructor button if you ever need anything. And that's all, folks. See you tomorrow.